Okay, well, we have some homework due today, so we'll start off by asking if there's any questions. Oh, and the one other thing that I wanted to emphasize is that you need to hand in your program as a jar file. JAR stands for Java Archive. Okay, so these are called jar files. And basically what it is, if you understand what zip does, to zip up a bunch of files, what's going to happen is when you do the project, you remember I mentioned that we're going to have a big project that you're going to do, and it'll have many, many different files. In Java, each class, the convention is each class has its own file. And NetBeans is a really good IDE. Remember what IDE stands for? Integrated Development Environment. It's a really good IDE for managing all those big number of files. And then, but the main thing I want to emphasize, I don't know if you were able to read it, or I know some of you did because I've talked to you, but on the web page there is a detailed description of how to archive your program into a jar file, and then what you need to do is hand in that jar file. Okay, now in this particular case it's really a little bit of overkill because there's only one file. There's only just one main class, and so to zip it up is kind of ridiculous. But I want you to know how the process of making a jar archive. Now there's another thing that I want to mention about that process. When you read about that process on the web page, the thing that is really important is that you don't include any of the .class files, because I'm not just testing your program. I don't want to just test your programs. I need to read your code. So you want to make sure that you include the code and not include the class files. And so the instructions on the web page show how to walk you through the process with NetBeans on how to archive a jar file, or archive your source files without including the .class files. Okay, so any questions now about, and then I guess you had some written homework also, right, with the NZVC bits and stuff. So any questions about either the exercises or the program? Did you say you had some questions?
Yeah, I was more just how to get started with the program. We have to make it output next 10 numbers in sequence, right?
Right.
But there's a note here to go look at the attributes of the string class.
Yeah, there's a method called char@,
right,
and that's how you get an individual character. So then it's just like in C++. You know how you can convert a character value to an integer value? Mm-hmm. You subtract you subtract the character 1 and add. You remember how to do that?
No.
You want to check with me after class, or okay? Basically, what it is you see. Oh, we're actually going to learn the ASCII. We're going to learn ASCII today.
Oh, there you go.
Yeah, actually, let me postpone that. We'll a little bit later in the hour. We'll talk about that. In fact, I'll bring that. Remind me to
bring it up.
And yeah, to bring that up. How do you convert between ASCII and that? Okay. Any other questions? Is everybody good? Everybody's fine? So I don't think I'm going to bother to demo that method for doing the jar file because we need to move on. Yeah.
What does the printf mean?
Oh, that's a good, yeah.
Because I always learned print line.
Yes. Now I have found over the years in doing this project that there is printf is just very flexible. Mm-hmm. And I recommend that I gave you the link to the Oracle documentation for Java, the class libraries, and you should look up. You should see and maybe do a little YouTube tutorials on how printf works. But basically, what happens is when you say, I'll give you a little summary. When you use printf, what you do is you have a string here. You can say like my age is, and then And then you can put like a, oh shoot, now I don't remember what the,
%1, I think.
yeah, no, was it a percent D?
And a QT, it was %1, that's the reason why.
Is that what it is? I forget, I think it's percent D, I don't remember for sure. And then comma, and then you could put the variable, you know, age. So, oh, you did this did you do this style
We did
output?
.arg. And
Yeah, it's like the .arg. It's exactly like the .arg. And what happens is, whatever the value of age, whatever the value of age is here, it gets converted to a string and put in here, and then it says my age is, you know, 23, and then, you know, like space period, you know. So it'd say, if the value of age is 23, you'd say it would say my age is 23 period, and so it put this in here. Yeah, it's like the arg thing.
Okay.
Yeah.
So is it wrong if we just did print?
Not for now, but I encourage you to use Printf, because it's going to be, you're going to have to print out a listing, a program, and the flexibility of using Printf is really nice.
And it doesn't go to the next line, it would stay on that line. Like,
Right, if you wanted to go to the next line, you'd be bash n for new line.
Because does print line go to the next line?
Yeah, yeah. But I think it's better. This is just so flexible, and it's kind of like the C style, and Java didn't do it this way for a long time, but finally people said, you know, we need to do it like this because it's just so powerful and flexible way to format your output. Okay? So are we good? Any more questions? What about, was written problems all right? Written exercises okay? Okay, you want to hand those in? Okay, so we need to finish up chapter 3 and start chapter 4 today. So now, the next concept we need to learn is this language called, oh, I could ask the cameraman here to see if he remembers. We have a new cameraman temporarily for today, but I won't. RTL. Register, transfer, language. Okay, so a register transfer language, there are many different versions of register transfer languages, and they are all, so the RTL stands for register transfer language, and they are all used to specify the behavior of hardware. A register is a cell in, oh, you know what a register is, right? A register is a cell of, it's a storage cell in the CPU. That's what a register is, okay? And we're going to introduce registers today. We're going to look at the content, look at the organization of a CPU today. But, and so in order to be precise, to give a precise description of what happens with an operation in the hardware, register transfer language is used. Now, there's a whole lot of, there is no one register transfer language. It seems like every manufacturer who puts out a specification for their central processor uses a slightly different notation, and so there's no one particular standard. So this register transfer language that I'm showing you here on figure 3.17 is sort of like a combination of many common notations from, different register transfer languages that are common in the industry. But they mostly look very similar to this. Now, so let's go down this table in figure 3.17. You know from formal methods that conjunction is and. That's the same symbol we used in formal methods. And then or is disjunction. Exclusive or, I think we saw that. We've seen, no, that was the other class.
I've never seen that symbol.
Yeah, okay, the plus with the circle around it, that's the symbol for exclusive or. Okay, and then not is the same symbol that we're used to in formal methods, as well as implies. Now, the single stem left arrow is the transfer operation. And it is the hardware analog. It's analogous to what in the software, do you think? What? It's the transfer. In other words, it's...
Oh, gets?
Yes, that corresponds to gets in software, which in C++ and Java is the equals symbol. Okay, so we use this left arrow for transfer. And then the angle brackets, that's the bit index. So in a cell, the bits in a cell are specified, a particular bit in a cell is specified by the angle brackets. So let's suppose that we have a cell like this. This is 1, 2, 3, 4, 5, 6, a 7-bit cell. And then the individual bits in a cell are specified exactly the same way they are as an array in C++. In other words, this is sub 0, this is sub 1, this is sub 2. So 0 is the most significant bit in the cell. But we use angle brackets when we're talking about a register, all right, instead of square brackets, which is like an array in a higher order language. Does everybody see how that works? Okay. Braces are used, sometimes we need to get a little informal, so braces are used to enclose an informal English phrase to describe the operation. And now here are two important ones. The semicolon is the sequential separator, and the comma is the concurrent separator. Now those of you who haven't had programming paradigms, you know, what does concurrency mean? Two things doing what?
Something at the same time.
Yeah, happening at the same time, so simultaneously. So if you have, is everybody clear on that? So whereas the semicolon, if you have some statement here like this, and then semicolon, and then T, what does this mean? What does this operation mean? First S happens, and then after that, T happens. But if you have it like this, S comma T, what does that mean? S and T happen at the same time. Now, is everybody clear on that? Are we good? Okay. Now, so here is an RTL specification of the OR operation. Now, do you remember when we did the OR operation last time? We had, like, suppose you have a 4-bit cell, 0, 1, 1, 0, 0, 0, 1, 1, and we did OR. Remember how we did this? And we did the OR. Well, what happens is, this is the RTL specification for the OR operation. Remember, what did we say? Which bits are affected here? Do you remember which bits were affected when we did the OR?
N and Z.
N and Z, right? Because there was no concept of overflow or carry, right, with the OR. So look, so here is the RTL specification of the OR operation. So how would you do the OR of this? How would you do the OR? What would this be? 1, 1, 1, 0. And here, and then we have N and Z. And what would N be?
0.
0, because that's a copy of this. And what would Z be? 0, because they're not all zeros. Okay, so in this particular example, this is A, this is B, this is C, all right? And how do we read that? Yeah, C gets A or B, you know, so that would be bitwise. And then N gets, now what is this? C less than...
If it's negative?
Yeah, if this C is less than 0. If it's negative, then N gets 1. Otherwise, it gets 0. Are you with me on that? So everybody, can everybody read that all right? Yeah? Question?
It's talking about the whole value of it, like so.
Yeah, C is the whole one.
Like in decimal terms, or like in the value of the number.
Now, what is your question again?
Isn't N only the first?
And
Significant bit?
yeah, I know, but in RTL specification, it's if this whole thing considered as a signed quantity.
Okay, that's what I want.
Oh, that's what you wanted to know. Right. Yeah, that's kind of implied.
number.
Yeah, you're right. It is kind of implied, yeah. Yeah, so when we talk about the N bit only makes sense when you interpret the bit pattern as a signed entity. Yeah, good point. Okay, and so yeah, that's not on here, but that's implied. And then what is Z? Z gets C equals 0, where this, you know, if this is all zeros, then Z would get 1. Now, does everybody see how to read that RTL specification of the OR? Okay, now, two other operations that we're going to have to deal with, or maybe 2 or 4, I don't remember, The next operation that we're going to have to deal with is what is called the arithmetic shift left. Arithmetic shift left. And what do you suppose the letters are for arithmetic shift left? ASL. All right? Now let me give you an analogy with a decimal value. Suppose we have in decimal, suppose we have the number 563. Okay? Now, what does this figure 3.18 look like it's doing? It looks, what's coming in on the left?
Zero.
A 0 is coming in on the left, and then what's happening to every?
It's getting pushed to the left.
It's getting pushed to the left. All right. So now in decimal, if you have the value 563, and you shift each one, you shift the 3 over to where the 6, and the 6 over to where the 5, and the 5 over here, and you put a 0 in here, then what you get is 5630. Right? Now tell me, what happens to the value of a decimal number when you shift it left one position?
It's multiplied by 10.
It's multiplied by 10. Now why is it multiplied by 10? Because decimal is base what?
10.
Is base 10. So what do you suppose happens when you shift a bit pattern left by 1 bit?
Multiply by 2.
It's multiplied by 2. Are you with me? So let's just do an example. Let's suppose we have a 5-bit cell. And if we do ASL, so here we'll do an example of a 5-bit cell. So if we do an ASL of 01101. So what does ASL 01101 do? First of all, what would this be if you did an arithmetic shift left?
11010.
11010, and C would equal what?
0.
0. Does everybody see how that worked? Because according to this figure, what happens to the sign bit? The original sign bit of the bit value. It goes to C. Are you with me? So for example, if we did ASL 11101, what would that be?
It'd be 11010.
11010. But then in the end, C would be 1. Now, does everybody see how that worked? That's the arithmetic shift left operation. And numerically what it does is it multiplies by 2. Now, can you understand? Now can we understand? Yeah, question?
How did, for example, the 5-bit cell that was positive result into a negative number when you shifted to the left?
Yeah. What happens when you what do you think? Why do you think that happened?
Well, because of the overflow.
Yes. This was an overflow condition.
Okay.
Yeah.
But normally it would just double it.
Yeah, right. See, yeah, what happened was this one got shifted into this bit, and so it, what is this number? Let's calculate it. What is this number?
5
13.
plus 8.
13.
13, right? Yeah, this is 13. Now, what's the largest positive number you can store with in a signed one?
Oh,
0,
Yeah.
1, 1, 1, 1.
15.
15. But 13 doubled is what?
26.
26. So that's out of range.
Right.
So you see, even though the original was in range, if you do an arithmetic shift left, we got an overflow. So oh, wait a minute. I guess I was a little incomplete here, because what does this RTL specification say? Not only does the C bit change, not only is the C, we have to do what?
NZ.
NZ,
V.
yeah, actually NZVC, yeah. We have to do all of them. So, N, Z, V, well, let's just do it like this. Let's abbreviate it. It's a little less verbose. N, Z, V, C equals, and here we do N, Z, V, C equals. Yeah. Okay, now, so now in the end, what is N? In this case, in the end, when we do,
One.
it's 1, right? And what is Z?
0.
0, because they're not all zeros. And what is V? In other words, did an overflow occur when this was considered to be a signed number?
1. So yes.
So yes, an overflow did occur because we started with a positive number and we ended with a negative number. So that's how we know that that happened. And then what about C?
0.
We already said that the carry is 0, right? And then what about this one? N is, this is 1. Z is 0 because they're not all zeros. V
0.
is 0 because it didn't overflow. Because what did we have? Oh, let's do this one. What is this negative number? What negative, remember how to do the negative numbers?
It's negative 2.
No, it's negative 3. This one's negative 3, right? Because it's this, the place of this value plus 1 is 3, so it's negative 3. And what is this? 1 plus 4 is 5,
Plus 1.
plus 1 is 6, so this is negative 6. So sure enough, negative 3 got doubled to negative 6. Ooh, nice, huh? And so this is 1, 0, 0,
1.
and C is 1 because that 1 bit got shifted out. Oops, 1. 1, 0, 0, 1. All right? So does everybody see how, now, can we read the RTL for this? So C gets
What was an R0?
R0, and what's the comma?
0 through 4 gets
At the same time, R0 through 4 gets what? R1 through 5, and at the same time, what happens?
R5 gets 0.
R5 gets 0. So notice that this is not like in a programming loop where if you move this over and then, you know, it's that all happens at the same time. So nothing collides. Are you with me? Yeah, good question. We will learn how to do that in computer organization.
Oh, okay.
Yeah, that's, but in this course, it's a mystery. It's a lower level of abstraction. And what is abstraction? Hiding details. So those details of how that does it are hidden. Yeah, but that's, yeah, in fact, that's going to be a really important detail that we're going to examine in lots of, you know, thoroughly. And then what does a semicolon mean?
Sequential.
Then
After that's all done, after that shift takes place, then what is the value of N? N gets what? The finally R's less than 0. Z gets R's less than 0, or sorry, R's equals 0. And now here we have an informal specification. What do we say, V?
it's over.
It's over. So how did we, that's an informal description of what we said happened over here, right? We said, well, if it's negative, you know, so we don't formalize those rules. We'll just keep it informal. Are we good? Does everybody see how that worked? And now, this is an arithmetic shift right. Okay, so check this out. Here again, I can reuse some of my. So arithmetic shift right is obviously abbreviated what?
ASR.
ASR. Now, what happens if we'll do our decimal example again, 563. Now, if we do an arithmetic shift to the right, then where does the 5 go? The 5 goes to where the 6 is, and the 6 goes to where the 3 is, so what would we have? What would we be left with? 56. Now, what are you doing when you do an arithmetic shift right in decimal?
You're dividing by 10.
You're dividing by 10. But it might not be exactly by 10 because unless this number is 0, are you with me? If this number is 0, then it's exactly divisible by 10, and when you divide by 10, there's no remainder. And yeah, and that's what it is. It's the floor. Okay? So, by analogy, since binary is base 2, what happens when you do an arithmetic shift right in binary? You cut it in half. Might not be exactly in half because it might be an odd number. But now look, you guys, on this figure, what is this little Okay, first of all, where does the rightmost bit go? The least significant bit, that goes to the what? That goes to C, right? But now what do you think this means? This little loop. It maintains its same value. Now why would you want it to maintain its same value?
Because half of a positive number is still a positive number, and half a
A
negative.
negative number should still be negative. So the sign bit is duplicated. Does everybody see that? How that works with the arithmetic shift right? So let's do an example again with a 5-bit cell. Oh, and by the way, the RTL specification is a problem for the student. Okay, so based on that picture. So let's say we have 0, 1, 1, 0, 0. 1, 2, 3, 4, 5. And let's do an ASR on this. So if we do an ASR on 0, 1, 1, 0, 0, what will we get?
0, 0, 1, 1, 0.
0, 0, 1, 1, 0, right? And furthermore, N, Z, V, C will equal what? Actually, before we do that, let's check the decimal values. What is this decimal number? 1, 2, 4, 8. What is this decimal number? Or what is this number in decimal? It's 12, and what is this one?
6.
And sure enough, 6 is half of 12. Yeah? And now what about this? N, so what, N is what?
0.
0. Z, 0, because it's not all zeros. V, did an overflow occur?
No.
No, we took half of 12, and that's 6, and that's fine. So there's no overflow. And how about C?
0.
0, because this 0 went there. Oh, it's all zeros. Okay? Are we good? Now, how about ASR of this? 1, 1, 0, 0, 1 equals, now what is this?
1, 1, 1,
1, 1, 1,
0,
0, 0. Okay? And now what is our NZVC on this one?
1, 0.
And let me see. N is 1, because that's the copy of this final one, right? Z,
0.
0. V,
Oh,
Will
0,
it always
sorry.
be 0 for these?
oh, actually, haha, that's a good point. It will always be 0. Why is that? Because you can't overflow whenever you
Half.
cut it in half. So guess what, you guys?
V isn't even
V is not even, so it's NZC. So I shouldn't have done this. I should have left off the V here. My mistake. The V bit is not affected by the arithmetic shift right. I got a little careless there. And now, and what is C?
1.
1. Now let's verify. What is this number? What is this number originally, if it's a signed quantity?
Negative.
See, 1, 2, let me see, what is this? 2 plus 4 is 6 plus 1 is 7.
Seven.
So this is negative 7 ahead of time. This is negative 7. And then, and what is this?
This is negative 4.
Yeah, this is negative 4. Well, 4 is roughly half, negative 4 is roughly half of negative 7. But it's the floor of it. You know, it's to the left.
No.
Are you with me on that? Is everybody good on see how that worked?
If it was 7, it would go to 3. Not 4.
This is negative
If
7. It
it
goes
was
to,
positive
Positive
7?
7 would go to 3.
oh, if it's positive 7, it would go to, yeah,
It would go to
it
3.
would go 3, yeah. You can work that out. I think that's what happens. I'm pretty sure that's what happens. You should check it. All right, is everybody clear on how the arithmetic shift left and arithmetic shift right happens? Now, the next thing that we want to do is we want to learn how to use the hexadecimal system. Now, hex means what?
16.
Yeah, hex means 6, decimal is 10, so hexadecimal is 16, base 16. Well, so here's the story. If we were born with, instead of 10, and I wish that we had been born with 8 fingers on each hand. That would have been so much better. All of our scientific measurements would have been, it would have been simple. Everything would be divisible by 2 and then divisible by 2 again, and all of our decimal number system. There are so many advantages to counting, to having your number system be in base 16, but unfortunately we have to go with what nature gave us, which is base 10. But but if we did have 16 fingers, when we got to, 0, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, this would not be our last finger. So we would keep doing what? No, not 1, 0, but we would have to invent a what?
New digit.
A new symbol,
Like A.
like A. And then the next one would be what? Another new symbol, like B, and another like C, and then D, and then E, and then F. But now, by the time we get to F, what number are we at? In decimal.
16,
15.
15. So 15. So that would be 1 before our last digit. And then what do we do with our last digit?
Carry it over.
Yeah, that becomes the 1, 0. Are you with me? So look at here how we count in hexadecimal. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And then after F, it's 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, 1, A, 1, B, 1, C, 1, D, 1, E, 1, F, 2, 0, 2, 1, 2, 2. Does everybody understand how to count in hexadecimal? All right, let's do a few. Let's count A, 5, 7, D. Let's start counting, all right? So what's the next one? A,
5, 7, E.
E, A, 5, 7, F, A, 5,
8, 0.
8, 0. Is everybody clear? A, 5, 8, 1, etc. Yeah? So over here, what,
Oh, keep going.
no. We're going to start with another one. Okay, so now how about 1, 9, 9, D. 1, 9, 9, E. 1, 9, 9, F.
1, A, 0, 0.
1, 9, A, 0.
This,
Yeah.
are you with me? 1, 9, A, 0. Does everybody know how to count now? 1, 9, A, 1, etc. Is everybody good? Okay, it's over here. Over here?
Yeah.
Oh, it's on? Okay. 1, I'm afraid I'm going to give you off camera.
No, you're good.
Okay. Okay. Now how about C, D, F, E.
C, D, F, F.
C, D, F, F,
C,
C,
D,
D,
C,
E.
E, 0, 0. Are we good?
That's a very large number.
How large, actually here, let's figure out how large C, D, F, E is.
160.
Okay, yeah, let's figure out how big this is. Now with base 16, which place is this?
ones.
This is the ones. And what is this?
16.
This is the 16s. And what is this?
16 squared.
16 squared. And what is this?
16.
This is 16 cubed. Ooh, does somebody have a big calculator? So how would we figure this? Do you have a big calculator? Does somebody have a big calculator? Well, I mean one that has lots of digits on it. Oh, you have one on your, yeah, can you pull one up on your computer there? So now how would we do this? First of all, what's the value of E? Do you see what the value, yeah, yeah. E is 14, right? So what is this? This is 14 plus what? What's F?
15?
So
plus 15 times 16,
Yeah.
are you with me? Plus what?
Plus
What's D?
13 times 256.
13 times, 16 times 16 is 256? Okay, plus what?
12 times 4,096.
12 times 4096. 256 and 60, yeah, that sounds right. Ooh, what's this one? Can you, are we still good?
Yeah,
Okay,
you got the entire board.
okay. I thought you were zooming in.
52,734.
52,000, say it again?
52,734.
So anybody else can verify that? So for
Yeah.
posterity, we're
Thank you.
in good shape. Did I have a second to the motion?
Yes.
You got it, the same thing? Okay, good. I would hate to have a mistake go down. Okay, now, why do we use hexadecimal? And here is the principle. And by the way, we just abbreviate this hex, okay? So hex is an abbreviation for binary. That's why we use it. And the reason we use it is because there's a very special relationship between hexadecimal and binary, which is why I wish we had. Oh, here's figure 3.20. Here's an example of how to do 8BE7, but we just did that example. All right. And in figure 3.22 is a table that that shows this special relationship between hexadecimal and binary. Notice that in binary, if you have 4 bits, the number of possible combinations of 4 bits is exactly what?
16.
16. You can read them out as 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. Those are the 16. Those are the 16 possible combinations. But look, in hexadecimal,
We have
exactly 16 hexadecimal digits.
so one
characters.
symbol can represent any one of those combinations.
Yes. And so so now do you see why it's an abbreviation?
Yep.
Why write down, I mean, look how stir crazy it is. To write down a whole sequence of ones and zeros. It takes up a lot of room on the page. We want to be green. We want our information to not use as much paper. So we use hexadecimal, but it's just an abbreviation. Now, it's a pretty straightforward question.
The color codes in for colors is the 6 digits of hexadecimal.
Yes.
Colors?
Yeah, but that's a binary. Yeah, that's actually a
It's
binary.
really long binary.
Yeah, yeah.
That's kind of cool.
Yeah, that is.
That's kind of cool.
Okay, so now look. So here's how you do it. Suppose we have a 12-bit cell. All right? And suppose that the value that we have in this 12-bit cell is something like this. 1 0 0 1 1 0 1 0 0 1 1 1 2 3 4 5 6 7 8 9 10 oops 1 2 3 4 5 6 7 8 9 10 11 I need another one. 0. Okay? So suppose we have this value in a 12-bit cell, and we want to write that, and we want to abbreviate this and write it in binary. What you do is you start from the right.
Take the first 4.
Take the rightmost 4,
6,
then the next 4.
A,
1 2 3 4 5 6 7 8 9 10 11. Oh, this was not a good example. I wanted to do something different. Okay, and so how would you write this?
6.
You would write this as what?
9A6.
Yeah.
9A6. But now what if you have, instead of a 12-bit cell, what if you have like a 14-bit cell? Okay? And this 14-bit cell you have 0 1 0 0 1 1 0 1 1 1 0 1 1 2 3 4 5 6 7 8 9 10 11 12 13 14. Now what do you do? How do you write this? Again, what do you do?
Section.
You start, yeah, you say, but you always start at the right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And now it's like this. Are you with me?
Okay.
And then, now what is this value? What number do you put here? Well, for purposes of the abbreviation, you do it as if this were what?
Zeros.
As if they were zeros.
Right.
Is everybody clear on that? So this would be 1, 3, 7, 5. Are we good? Now notice that you never use a negative sign with a hexadecimal value. Right? Because the sign bit is in that binary thing, right? So because it's just an abbreviation for binary. Right? And now here in figure 3.21, there is a table that just counts up in decimal in the body of the table. And if you want a really quick way to convert to hexadecimal with, you know, with just up to from 0 to 255, you can just look this up in the table. For example, what is the decimal value of 9E? Well, you go down there to 9, you come over to E, and it's 158. So that's a handy little table you can refer to if you want. Okay? Is everybody clear on how that works? And how hexadecimal works? Oh, and now one more thing. Oh, shoot. We got to get to the next chapter. And now here is the does anybody know, this is the ASCII table. Have you ever guys ever heard of ASCII? ASCII. Does anybody know what it stands for?
Abbreviated? No.
American
Standard character.
Character.
Standard Code
Age.
for Information Interchange.
Yeah.
That's what it stands for. And it was used in the old days. They, you guys, have you seen these old Western movies, black and white Western movies from the old days? And they had, you know, like they had like a teletype machine. Do you know how,
Yeah.
or a telegram, you know? And so what they would do is they would send these binary signals over the. This is before computers. Well, it's not quite like Morse. So Morse code is da 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 da. Yeah, I used to actually know a little bit of Morse code. My dad was a amateur radio operator, but so what they would do is they had to have a way of sending text. You know, like you would send this over, and then it would come out at the other end. It'd be a telegram. You know, have you guys know what a telegram is? Yeah. Okay, so they would send. So they would send this code, and it was a 7-bit code. All right. And and you can see here's the chart that shows all the possible values of ones and zeros with 7 bits, right? And so, and for example, to send the letter K, how would they send that in binary? Well, you just go down here to K. It's 110 1011 110 1011. So that's how the letter K was stored. Right? So what happened is when computers were invented, they just adopted this code to do the letters, to do alphabetic information. Yeah? But now, because in fact, all computer memories store how many bits in a byte? 8 bits in a byte. So what they've done is they extended the ASCII code and they stuck an extra letter on here, and that's how you get the accented letters. Okay, that's the extended ASCII code, but I didn't show that here. But you know, you have like umlauts over the O for German language, and you know, accent marks for French and whatever. Okay, so but ASCII, the original ASCII code is a 7-bit code, and not all of these codes are printable. In fact, on the next part of this figure, figure 3.23, these are the non-printable things. Now, do you know how, there's kind of an interesting story here. Since it looks like we're not going to get to the next chapter anyway, I might as well do a little trivial. Here's a Trivial Pursuit question. Okay, you know how? Have you seen pictures of how these teletypes worked? Yeah, well, I mean, you guys have seen typewriters.
Yeah.
Okay, that's your. I mean, I'm not that old. You guys have seen typewriters.
Yeah.
Okay, so you know,
One.
you've actually used one.
And radio too.
Oh yeah, they're still around.
For that.
Okay, now so what is that round cylinder called?
Cartridge.
No, the round cylinder that moves the paper through.
through?
Yeah. Well, I don't even. Yeah, actually, I was going to say it's the carriage, but it's actually not the carriage. The carriage is the. Oh yeah, it is. No, you're right. It is the carriage. It is the carriage. Yeah. Because the round thing. But what happens is the keys type it, and the carriage goes as you type, right? And then what happens when you get to the end?
Drops
You,
that line.
yeah. Now how did that handle work? You'd push that handle, and that would push the carriage to the right, so that you could start typing on the left side of the page. But what else did it do?
It drops it down.
It also did it. It also moved it. Well, those teletype machines had to do the same thing. They had a carriage, only with the teletype machines, the key thing moved, right? But then they had to rotate it to go to the next line. So to go to the start of the next line, you had to do two things. What did you have to do?
Move it back to the front.
You have to do,
down.
yeah, you'd have to do a line feed, which was the rotation, and the carriage return, which is. So look here. Where's LF? Do we have an LF?
Yes.
That's the line feed. That's what controlled the rotation, and then the what? The CR did the return. You know, made it go to the start of the next line. So guess what? At the end of each sentence, they always had to send, for the teletype machine, they always had to send what? A line feed and a what? Carriage return to go to the start of the next line. Line feed, carriage return. Line feed, carriage return. All those signals. So you know what Microsoft did?
Enter.
Whenever they decided how to adopt their, you know, you know what they did? Whenever they decided how to adopt a standard for their text files, at the end of each line, what would they put? A line feed and a carriage return. Even though with computers they're electronic, there's no more carriage. Whereas the Unix people, what did they do?
Just a line.
Yeah. Because there's no more carriage, we don't have to do both. So they're going to start on there's just one character. And that's been, you know. So, you know, you have these extra characters still. I still get from people who have Windows computers, I get text files from them, and I see these two, you know, sometimes the software isn't intelligent enough to know that a line feed carriage return because it's
Oh, really?
oh yeah, I get you know, you get the extra, that extra thing, and I actually even have a program in C that'll go and strip out everything except the new line character, because it shows up, it'll show up in like in VI or something, you know.
Right.
Yeah. So anyway, that's the story. And you know, notice that space is a character, delete is a character, which makes it go back one, and or backspace. And there's acknowledgement. You know, there are control signals. They had to control. Did you get this? Yes, I got it. So they would send a signal back and forth. You know, and so those are all these control signals. And if you go back over here, you see that those are the codes, the big ones. Null is 0000, and SOH is start of header. I think it's start of header. Yeah, start of heading. STX is start of text, ETX end of text, and so on. And BEL, that would ring the bell. They would send that code, the BEL code, which is what? 07, and it go ding. So people, and you can still do that in some output routines. You know, you send that to the output, and then when you think if you want the screen to beep and beep, it'll beep. So if you had a program that outputs that, and your terminal's emulator, you know, knows how to interpret all of those codes, it'll actually beep. But we've gone way beyond. I mean, now with, you know, sound files and all that kind of stuff. All right. So that's the story of information representation. And you do have a homework problem that's due on Monday that is, requires you to read the first part of chapter 4. But I think you can read that. It's pretty straightforward. We'll go through it really quickly at the beginning of class on next time. But I encourage you to read ahead on that. Okay? But it's pretty simple. Oh, although I do think there's another problem too. I think there's another program. But it's also similar to what you did this time. Okay? See you next time.